So up here, I went ahead and I'm going to open that door just in case when people come and see. I want to talk about theoretical yields, and it's a specific stoichiometric calculation. And actually on the board, I went ahead and put clear back when we talked about balancing equations. We said this one's balanced if we put 2 from the MG and then 2 from the MGO. It's balanced, and we said we could do a stoichiometric calculation. You should have this in your notes where if we, did I do that wrong? Oh man, it still seems weird. I guess it's right. Make sure I don't butcher this. I was trying to kind of draw from what we did before. And then did this one. Yeah, I have that wrong. Okay. You can kind of see it on the board. We actually went from 0.30 grams of magnesium to sufficient, we'll talk about this more on what this means on Wednesday, sufficient amount of oxygen, and we said that would give you 0.50 grams of product. And what that specific calculation is what we call a theoretical yield calculation. Anytime you're going from the mass of course we have 2 reactants and 1 product, okay? Anytime you're going from the mass of a reactant to the mass of a product, such as this, you are calculating the theoretical yield. Now, I don't know about you, but when I think of the word theoretical, I think of, that's what it's supposed to be. It's theoretical, okay? So theoretical yield is just, like I said, calculating the mass of a product based upon a stoichiometric calculation. Now, excuse me, the theoretical yield actually, as it turns out, is generally an upper limit to what you can get back. So I have several slides to show you why, if we did this, if we ran this with 0.3 grams of magnesium with sufficient oxygen, we probably would get less than 0.5 grams of magnesium oxide. I'll show you many reasons why that would be the case. So this is what we say, just kind of generally an upper limit. So when you really run the experiment, why do you get less than 0.50 grams of magnesium oxide? And I'm going to talk you through each one of these. One is reaction kinetics. It has to do with the speed of the reaction. One is that it might exist in equilibrium, might be going back and forth from left to right, although this one isn't. This one actually does have a competing side reaction, so basically some of your reactants go to form other products. You might actually, during the course of the experiment, have something in your experimental design that's just, you lose some of your reactant in the step. So starting with reaction kinetics, we assume when you turn that light on, electricity will flow through the light bulb, and that will actually excite the gas atoms, the electrons around the gas atoms, so that they are excited and they fall back down, and right away when you turn on the light, we see the light. But actually, light travels at a discrete speed of light. And in the star that's located 1 light year from us, actually it takes 1 year for that light to get from that star to us. So kind of like that with experiments, we think that a chemical reaction just goes like that. There's a whole actually side part of chemistry dealing with what's called reaction kinetics. How long does it take to, what we say, proceed from reactants to products? Okay, so basically if you get antsy and if you squelch your reaction, if you grab your product and go, maybe you didn't give it enough time. So this is actually a graph showing you a chemical reaction where the red represents the reactants. And you kind of see this is concentration, where it's actually decreasing over time. The red is decreasing over time. Time is along the x-axis, concentration is along the y-axis, and the green is the product. So you see the product kind of creeping up. And what this slide says is if we were to squelch it starting about 7 seconds, 2, 4, 4, 6, about here, 7 seconds. That actually is the intersection of the reactants decreasing and the products increasing. You're looking at about, you're only halfway through your reaction if you stop at 7 seconds. I don't know about you, but I get impatient for my toast to come up in the morning. So 7 seconds might be, I just can't wait. Reaction kinetics, did we give it enough time? Chemical equilibria is something, it's a player in chemistry, and it's a reaction, not this one, but a reaction goes from left to right, like I've written this one, but a reaction also goes from right back to left again. In my general chemistry 2, we're talking about this chemical equilibrium right now. H2O, actually normal water, will, what we say, break apart or auto-ionize. It will go to form 2 hydrogen ions, one hydrogen ion and 1 hydroxide ion, okay? But it will also reassemble, okay? So it's going from left to right and from right to left. That's the kind of what we call the chemical equilibrium arrow. So that's the auto-ionization of water. So if that's the case, we're never going to be able to, it's like a moving target. It's never going to go to what we say completion. It's going to be going from right back to left again as well. Okay. So I have an example to show you here. Up at the top, you see the equation representing the equilibrium, where we have H2 and I2, those are our reactants, going to form HI. That's our product. And this is balanced with a coefficient of 2 in front of the HI. But you can see actually, again, we have time along the x-axis and concentration along the y-axis. So as we start out, notice we have all of the reactants, H2 and I2, and none of the product. Let time unfold, and notice that actually at some point I can draw a line here, maybe about here, where we kind of deadpan the concentrations. That's to say the amount of HI we're going to reach is constant. That's what we say in equilibrium. And the amount of H2I2 left is also deadpan. But this is a good example of, will it go to what we say completion? Will, at the end of the experiment, will we have no reactant left? And the answer is clearly no. It's what we say dynamic equilibrium. It's still kind of going back and forth even as we speak out here, but the concentrations are constant. So yeah, you're never going to get your yields, will never be 100% just because of the nature of the equilibrium. Here's one, again, you can't control. What if there's a possibility for it to do something else? When I say it, I mean the reactants to do something other than what you wanted. A real common one here is when you guys were burning your magnesium strip. Of course, you would tell me in this room we're about 20% oxygen, about 80% nitrogen. So an unwanted side reaction would be for your magnesium to actually react with, nitrogen gas to form magnesium nitride. Mg3 and 2. Okay, so it's an unwanted side reaction, which means that for sure you're not going to get all the magnesium oxide you thought you were going to get, because some of it is magnesium nitride. So, you know, these are all reasons why your theoretical yields, why when you go to do your actual yield, it's going to be less than your theoretical yield. The actual yield is what you get in the lab. One of them then is what I say kind of inherent in the design of the experiment itself. And we actually we lose a lot of our reactant the more steps we lose if we have multiple steps in an overall chemical reaction, then you're gonna maybe lose some of your stuff between. Okay. In pharmaceuticals, they are very picky about having no impurities, and so actually, oftentimes in pharmaceuticals, yields are very low because of a purification step, but that's just the way life is. Okay, so these theoretical yields are just a stoichiometric calculation, and again, it's what you would get if all the stars aligned. Okay, it's what you would get if all of your, and we'll talk more what a limited supply reactant is, but all of your reactant, of your special reactant reacted, and if there were no other side reactions, okay, and if you were able to grab all of it. So like I said, I mentioned the purification steps. Okay, we lose a lot of it. So I mentioned that, what was it here? Physical losses are not the same thing as gross errors. Gross errors are the oops. Gross errors were not inherent to your the design of your reaction, or design of your experiment. They are not inherent. You introduced them. So, so for instance, if you spill some material along the way, that's a gross error. That's oops. It wasn't in your write-up. Okay. If you misread one of the things that you're measuring, it's an oops. That's not inherent, and it actually would throw off potentially what you end up getting back. If you calculate something wrong, okay, if you don't follow instructions, those are gross errors. So gross errors are associated with the experimenter, not the experiment. So let's do a calculation. There's this calculation called percent yield, and it's based upon your theoretical yield. It's a ratio of what you thought you should get back. So in the denominator, in the numerator is what you actually got back. So sometimes actual yield is called experimental yield. And like I was saying, the theoretical yield actually comes from the stoichiometric calculation. So actual yields is, you'll see me call it experimental yield. It's what you got back. And then the theoretical yield, this comes from stoichiometric calculation. Okay. So, for instance, we did a stoichiometric calculation. I think we did, yeah. We did before I turned you loose on that wild one that we ended with on Friday. But we said that if you have 1.25 grams of Cl2, we said you could do a stoichiometric and sufficient P4. You could do a stoichiometric calculation that, in theory, you should get 1.61 grams of PCl3. That's our stoichiometric calculation. So that actually is our theoretical yield. Let's say you went to the lab and you measured out that mass of Cl2 with sufficient P4, and instead of 1.61 grams, and I mentioned they're usually low, instead of that you actually got 1.08 grams. So that is what we call your actual yield. So, I can't spell yield, that's okay. So then in order to calculate your percent yield, all we're going to do, and actually you guys are going to be doing some of this in tomorrow's lab, all we would do is do a ratio. So don't make it harder than it is. So percent yield is simply the actual yield, 1.08 grams, divided by the theoretical yield that we got from stoichiometric calculations back on Friday. We round it according to 3 sig figs, and you're looking at 67.1%, which in a practical sense, that might exceed the expectations. If you're out in a plant doing, as a chemical engineer, they will have these numbers of your expected yield at the different stages. So it's not always 100%, kind of like what we talked about. So these will be due when we meet again on Wednesday. Finical? So what would you mean? Okay. All right. Very good. Well, it wasn't going to go on, but what the heck? Let's go on and finish this last concept. Okay. So when we did this calculation, I'll kind of erase everything but this one. We've been using the word sufficient a lot. That just means plenty or enough. Okay. Now it's possible that you go to your cupboard. Well, I'll put it this way, and I won't put up the whole recipe, but I think always. We said you could make brownies. I'm going to totally butcher this. I'll change it up. I'll make it cookies. You can get 12 cookies. If you have a quarter cup of butter, let's just pick a maybe 3. 1 cup of sugar. I don't know what kind of cookies they are. And let's say 2 eggs and some other ingredients. Okay, but let's just say these are the amounts of, these are kind of like our reactants that you need to make your product. And let's say you go to your cupboard and you see that you have 8 cups of butter and you have 2 cups of sugar. You see where I'm going with this. And you have 6 eggs. Sometimes I would call this my have amounts. So this is what we had in our cupboard. Just eyeballing that, do you guys buy this? That to me, it looks like what I will run out of first is my sugar. Okay, it limits me. You know, if I would go with my butter, dang, I could make, let's see, 8 times 4 is 32. I can make 32 batches. Woo. If I go with my eggs, I can make 3 batches. If I go with my sugar, I can make 2 batches. Okay, so this is actually our limited reactant. It is in what we say limited supply. And then guess what? These guys are both an excess reactants. They are an excess bulk supply. So, taking it one more step further or whatever, if somebody called me up and they're like, oh, we need cookies, and here's the recipe, how many cookies can you make? I'd have to say 24. That's about all I can do. You know, if you bring me more eggs or more butter, I might be able to do better. But I have to do that sort of yield calculation based upon what's in limited supply. I can't do anything else. You can't make it where it's not, and you can't change the recipe. Okay, that's the concept of identifying something, a reactant, that's there in limited supply, and that's also the concept behind saying it's the driver for how much product you can use, and it's also the driver in how much of the other reactants that you'll use up. So the limited reactant is a big one. So switching it from brownies to sandwiches, what if this is the recipe for my sandwich? For every sandwich, I'm just going to make a simple sandwich, 2 slices of bread and a piece of ham between them. Okay, so my reactants are my bread and ham, and my product is my sandwich. So I've got 20 slices of bread and 7 slices of ham. And then these questions would be like kind of what we say stoichiometric or questions about how this will go down. So how many sandwiches can we make? What do you guys think? I'm thinking 7, yep. Because I can't make 10. I could make 10 out of bread, but you don't have that much ham. So I'm just thinking 7. So if we make 7, how much bread will be left? 6 slices, because 7, we're going to have to do, for each of my 7 sandwiches, I want 1 slice ahead, 1 slice of, 2 slices of bread. So 7 times 2 is 14, so 20 minus 14 is 6, exactly. Is this your next slide? Okay. So switching it up. This is sometimes, there's a process of making ammonia. NH3 is the formula for ammonia, called the Haber process. So we're going to take 1 mole of N2 and 3 moles of H2 to form 2 moles of NH3. So I have a little video here. I probably won't play. One they haven't been playing this semester. That's okay. We'll go out and find it. If I have 6 molecules of N2 and 12 molecules of H2, I usually have to do the math. So 6 of N2, 12. Let's just do the video. Probably won't play.